Now, what we were talking yesterday in the last class was steady flow systems. Or steady flow system, we had applied that equation to boilers, condensers, nozzles, diffusers, turbine, compressors, throttling process, your reciprocating process, compressors, and mixing chambers. Okay, and in each case, what we did, we started from steady flow energy equation and applied the assumptions, or you can say specifics of that problem, and we derived the problem for that, sorry, equation for that process. Now what we are doing is we are using the non-steady flow energy equation, and we will try to solve some processes. Okay. Now, but I will start from the derivation again, because slightly you'll be more familiar with it. तो जो हमारा डेरिवेशन है ये वही है जो हमने लास्ट टाइम किया था. And what we are doing is that we have two systems, or rather we have one system, main system, and it has two openings. One is the inlet and one is the outlet. Now what we do is that to convert this system into closed system, at the beginning we take it the main system and the smaller mass which is entering in as one system, and at the end of the time we are considering the main system and the mass leaving the system as one system. So if you take it like this, there is nothing which has gone out and nothing which has come in, because what was going in delta t time is part of the system. Similarly, what was going out is also part of the system. Okay, so it becomes a closed system. So what we are doing is that we are considering the main system with mass m1 at time t1 and mass of the fluid entering the main system during the time delta t to t1 as one system. Okay. The time duration is t1 to t2, and the two masses m1 the main system and the mass which is entering in, that is considered as one system at t1. And similarly you have main system with mass m2 at time t2 and mass of the fluid leaving the system m2. During this you take it as the same system at time t2, another form of the system. So system has changed from m plus m1 to m plus m2. Okay, so it becomes a closed system. Now I said we will be using this equation because there are kinetic energies and potential energy involved. So instead of taking only the internal energy, we will use here kinetic energy as well as potential energy. These two energies will also be added to delta E. So your E would be U plus half mc square plus mgz. This is your energy of the system. Okay. So if you, then I said there are something work has to be divided in two parts. One is the shaft work and the flow work. Shaft work is the work which goes into the system or comes out of the system because of a stirrer churning in. It may be a rotor or a stirrer, right? It can draw the power. If the fluid is moving the rotor, you can drive the power. If the rotor is moving the fluid, you can input the power. Okay. So then there is also a flow work which is given as M2 P2 V2 minus M1 P1 V1. Now M2 P2 V2 is the work done by the system on the surrounding, and M1 P1 V1 is the work done by the surrounding on the system. System is doing work to push the mass out of the system into the surrounding, and surroundings are doing work on the system to push in mass M1 into the system. Okay. So your total work becomes this. Okay. Now you can say that Q minus W will be equal to change in energy of the system. So energy of the system is at the final state at time t2, it is J2 plus this. This is the final energy. The initial is J1 and M1 multiplied by this. Okay. And if you add to it the flow work, because this work has been divided into two parts. One is work is equal to your flow work plus shaft work. So here you have, this is the shaft work is gone here. Okay. And this is equal to M2 P2 V2 minus M1 P1 V1 minus V1. Okay. So finally you get this equation. Q minus Ws is equal to J2 minus J1 plus M2 H2 plus half C2 square plus GZ2 minus M1 into H1 plus half C1 square plus GZ1. Okay. This was the equation we developed for a steady flow also. And here onward we put the condition that it's a steady flow. So J1 will be equal to J2, M1 will be equal to M2, and you get the equation Q minus Ws will be equal to M into delta H plus half delta C square plus G delta Z. That is the equation we got, and we used it for all the process. But now we will stop here and use this equation onwards when the system is a non-steady flow system. So something is going in, something is coming out. Okay. And they are different. So what is going in is different from what is coming out, right? So the main system is also changing. J1 is not equal to J2, M1 is not equal to M2. Okay. So now when we apply this equation, okay, we will skip this. I am skipping this formula, and it is nothing but the same formula. Only thing, if you have variation in the properties of the fluid when the mass is entering in over the space as well over the time, your M1 which is entering may not be uniform, and the delta T time which you are thinking, during that time the mass entering in may not be uniform, may not be constant. Its properties may not be constant. Then you'll have to do the integral. Okay. So what you do at that time, you see, integrate it over the area and integrate it over the time. So basically we want to find out how much energy which has gone in. Similarly, sorry, this is what is coming out, and what is going in is A1. So you can integrate all the energy which is going in over the area of the inlet A1 as well as time delta T to T1 to T2. Okay, this is what you can do. But that would becoming slightly equation more complicated. You can revert back to the earlier equation where we are thinking that at least in delta T properties are uniform or properties are constant. Okay, so let us apply this equation. Yeah, you can divide this equation by delta T also. So you will get Q dot minus Ws dot, heat given to the system, work done by the system, shaft work, and this is the change in total energy of the system. Okay, then this is the, you can say, the rate of energy leaving the system, and this is the rate of energy entering the system plus the flow work. So because U is replaced by H, so flow work is also accounted for here. Okay. Now let us apply this to this problem. Now we are trying to solve two problems. One is that of emptying of a vessel, and the other one is the filling up of a vessel. Okay. We are going to make lot many assumptions so that final formula we get is mathematical, and you can say brief and small formula we get. So this is a specialized case. You can see that both these problems have lot many assumptions, and so they may not be generally applicable, but we know how to do the problem. More problems more complicated than this will not be part of, we will not be covering them. Okay, so it's just to give you an idea that how do we solve a problem which is a non-steady flow problem. Okay, I don't intend to make it tougher than this. Okay, so let us talk about this. Now you see what we have done here is, this is the emptying of a vessel. So you have a valve here and you open this, and this vessel will slowly release its gas outside into the atmosphere. We want to solve this. Now J is the total energy of this main system. Okay, and J is the specific energy. That means per unit mass. So, and small j is equal to this. J means we are taking it as total energy, so it will contain UC square and GZ. Potential energy, kinetic energy, and internal energy. All the three are part of J. Okay. Now, what we are assuming that we are emptying it very slowly. So the properties are uniform in the vessel and at point A. This is the point A at which we are measuring the properties, and point B at which we are measuring the properties. Point B is the exit from the vessel, sorry, from at the, you can say, exit of the throttle valve, and point A is the entry to the throttle valve. Okay, but A is same as the main system. Okay, and this is why, because it is being emptied very slowly, so all the properties will be uniform in J. So this is another one assumption we have made. So J is equal to You can say UA plus half CA square plus GZ, and J is equal to MJ. So the properties at point A are same as the properties of the whole system. This is one assumption we are making. And it will be true if the process is slow. That means it should be quasi-static process, a very slow process. Okay. Now we come to this equation. Now if you look at this equation, the problem states that Q is equal to 0, Ws is equal to 0. So you can say the vessel is insulated and there is no shaft. So shaft work is 0. There is nothing entering in. So M1 is equal to 0, and of course C1 and Z1, they are irrelevant now. So what equation you get is, if you put all these, what will go away? Your this M1 will go away, Q will go away, Ws will go away. So what equation you will get? Okay. Yeah. Then we are also assuming this. There is another assumption that C2 is 0, Z2 is 0. There is another assumption. Okay. So we are making many assumptions just to be able to get the final formula which we want. Otherwise, we will not be able to get the formula the way we want it. Okay. Okay. So your final equation comes J2 minus J1 is equal to M2H2. Okay. Now, if you divide this equation by delta T, you get the equation. This will become dJ by dt. Okay. And this will become H2 into dm2 by dt. This is what you will get. Okay. Now you can break this into two parts. You will get m dj by dt plus j dm by dt plus dm2 by dt into H2. Okay. Now you also know the change in mass. This is mass of the main system, is negative of the mass leaving the system. There is nothing entering in. Otherwise, it should have been equal to dm1 minus dm2. But what we have done is we have made dm1 equal to 0. Nothing is entering in. Okay. So what you get here is, if you replace dm2 by dm minus, you get this equation, and finally you will come to this equation. Okay. Now J, you can yes, sorry, H2 we have replaced by this UB plus PB VB. Enthalpy is equal to U plus PV. Okay, and minus J comes as the. Now we are making another assumption that this is a throttle process and delta H is equal to 0. Throttling is delta H is equal to 0, but for ideal throttling, right? Where Q is equal to 0, Ws is equal to 0, and then you have the velocity at both the ends very small. There is no height change. So you get delta H equal to 0. So we are assuming the same throttling process, and we are also assuming that it is an ideal gas. Now, if you have ideal gas and it is throttling, then the temperature would remain same. That we will be doing in the end of this course. So if there is an ideal gas, then for throttling, because delta H is equal to, delta H would be equal to Cp delta T. And for ideal gas, Cp is constant, so your change in temperature will be 0. So you will find that there is no temperature change across A and B. What does that mean? That even the internal energy will be same at A and B, because delta U is equal to Cv delta T for ideal gas. These equations are for ideal gas. Okay. Because for real gas, Cp and Cv vary. They don't remain constant. For ideal gas, Cp and Cv are constant, and that is the assumption we have made. So if it's an ideal gas, isenthalpic process, temperature is main constant. So also the you will find that your internal energy will remain constant. Now your J, it was equal to, what was J equal to? UA plus half CA square plus GZA. Now we are assuming also that the main vessel is having, you can say, height is not much. Moreover, there is no movement of fluid inside. So both these terms are 0. So what is happening is your UB is cancelling out with J and you get this equation. Okay. Now, because TB is equal to TA, is T is the temperature of the vessel. Okay. So what we can write here is that, and PV is equal to RT, we can write this equation. What we have done here, PB VB is equal to RTB, okay, and this RTA, and this is RT. Because TB is equal to TA, being isenthalpic process, and TA is same as the vessel temperature. Okay, so we'll write it like this. One second, let me finish. Now DJ for ideal gas can be written as Cv dt. It's all simple mathematics and assumptions. Okay, so mathematics is not difficult. Assumptions you keep in your mind, and then you get this equation mCv dt, and this you finally solve this equation, you will get this T2 by T1 is equal to M2 by M1 raised to power gamma minus 1. So what we are getting from here, the temperature of the gas inside the vessel will change, and the ratio between them T2 by T1, and these are absolute temperatures. Remember, because PV is equal to RT uses absolute temperature. You cannot put degree C there. And the same T is carried over here. I told you right in the beginning, when delta T is there, you can convert Kelvin into degree C. But if it is T there, then you cannot replace T Kelvin by Celsius. That you cannot do. Okay. So what you get is this equation. What is this telling you? Now what is happening is mass inside is going down because it is going up. Volume is remaining same. If you see, I think this was equation TV raised to power gamma minus 1 is constant. Okay, whatever it is. So you get another equation of the similar form. Now it is the equation for temperature. So how the temperature would change? So you can find that if you are emptying a vessel which is containing ideal gas, which is insulated, there is no shaft work, it is slowly you are uh, removing the gas, then the inside temperature would be given by this. See? Now further you can do, you can you can use this equation, because inside pressure will also change. Inside pressure will be equal to P2 T2 V1 and P1 will be equal to M1 T1 V2. Okay, पर ये उल्टा लिख दिया क्या? P1 V1. Okay, yeah, ठीक है. You using this relation P1 V1 is equal P1 V1 is equal to M1 T1. Okay, and P2 V2 is equal to M2 T2. Now your V1 and V2 are same. V1 and V2 are same, so you get P2 by P1 is equal to M2 into T2 by T1. You put this equation into this, right? And finally you get this equation. T2 by T1 is equal to P2 minus P1 raised to power gamma minus 1 over gamma. And this is the same equation of isentropic compression or expansion. Okay, so you get this equation for emptying a vessel. So if you are given P2 and P1 and T1, you can find T2. What is T2? Or in this equation, if you are given M2 and M1 and T1, T1 is the starting temperature, M1 is the starting mass. If you know the final mass, you can know T2. Similarly, if you know the final pressure, initial pressure and initial temperature are known, you can find the final temperature. Okay, so this is what the equation. There is an alternate solution to this, and what we are doing here is we are introducing a hypothetical boundary enclosing the system. So what we will do, I'll come to the diagram and then tell you. Okay, let us see the diagram first. So what I am doing is I am dividing the whole mass into two parts. This is your M2 and this part is M1 minus M2. Okay, so the total mass is M1. Okay, M1 mass है. लेकिन we have divided that into two parts. Now this M2 will remain within the system and M1 minus M2 will come out. When you open the wall, M1 minus M2 will go out and M2 will remain within the system. Okay. Now you can assume that this is an imaginary boundary. Okay. And across this, there is no heat flow, because temperature is uniform everywhere. So there is no heat flow. Okay. So what is this expansion? This is a, you can say, adiabatic reversible expansion. Adiabatic, why? Because no heat is flowing into mass M2. Everywhere it is uniform temperature, so no heat flow from M minus M1 minus M2 part to M2 part. There is no heat flow. And the expansion is also slow. You are opening the wall slowly. Slowly and slowly the gas is coming out. The pressure gradient is also not much. It's a quasi-static process. So the mass M2 is expanding adiabatic and isentropically, or adiabatic reversibly. And what is the equation for that? T2 by T1 is equal to P2 by P1 raised to power gamma minus 1 over gamma. We are familiar with this equation. So all that analysis is gone, and we have solved it like this. Okay, so either way you do it, you get the same answer. And here now you can replace P2 comma T2. You can use this and V1 V and P1 T1 comma V. This will give you M2 and this will give you M1. And you can get back the equation T2 by T1 raised to power is equal to your in terms of mass, which we have got. You can try that equation and we can get this equation. ठीक है, तो ये हो जाएगा. Now we come to the next part of the thing. Yeah. We are filling up a vessel. Although in real life, mass may be entering in, mass may be going out. Both things may be happening. But then we will be stuck up. We have the equation. We will require more details to solve it. Okay. But writing in some mathematical, you can say concise form will be difficult. Because there we took the advantage of M1 was 0. Here we will take the advantage of M2 equal to 0. And still we'll make some assumption and we'll get the something. So you have a system, here's J, and something is filling in from the atmosphere. Now time interval is this, T2 to T1. Okay. Now this is our equation. I need not repeat it, same equation. Okay. And now given that Q equal to 0, Ws equal to 0, M2 equal to 0, and of course C2 and Z2 automatically become 0. So this is gone, this is gone, this is gone. What do you get the equation? And now you are assuming also that C1 equal to 0, Z1 equal to 0. This is the assumption you make. If you don't make this assumption, you will not be able to proceed further. That's the only thing. So just to make the problem simple, we make this assumption. So equation J2 minus J1 is equal to M1 H1. Now we make another assumption that the vessel is empty at the beginning. We are making another assumption that the vessel is empty at the beginning, which means M1 is equal to 0 and even J1 will be equal to 0. Okay. So what do you get? Now, even your M2, the final mass will be equal to what mass you have put in M1. Okay. So you get the equation J is equal to MC dVt, MCVT. तो ये आ जाएगा finally M2 CV T2 minus M1 CP T1 equal to 0. This is the M1 is the mass which is entering in. CP for H1 we have taken CP and T1. So H1 is equal to CP T1. Okay. And T1 is the temperature at which it is entering in. And you get on the left side is M2 CV into T2. Now you'll find that M2 is equal to M1 because the vessel is empty in the beginning. If that is the case, you will get T2 equal to this much. So if you are filling a vessel and if it is empty in the beginning, your final temperature will be equal to T1, the initial temperature, into Cp by Cv. Okay, so this is what you will get. So you can get this thing. So again, as I told you, and this is why it happens. You see, this thing is practically, you can see, when you are filling some vessel, it becomes hot. It becomes hot. What is happening is, when you are filling, you are giving thermal energy, or you can say the internal energy is M1 U1 T1. Sorry, M1 U1, that is being given in. But for filling the vessel, you are also doing some work on it. Okay, तो वो जो है उसके अंदर वर्क डन आ जाएगा. T2 by T1 will be equal to Cp by Cv. Okay. It next class. Anything you want to ask? हाँ, यहाँ पे हमने किया था. देखिए J जो है, J is actually equal to UA plus you have specific kinetic energy half Ca square plus GZA. ठीक है. Now these two we are ignoring, so it is equal to UA. But UA is equal to UB because it's an ideal gas. Throttling में there is no change in temperature, so the kinetic energy will remain same both sides. Sorry, internal energy will remain same both sides. Okay, so that is why it is good. Yes, anybody else? Okay, then we stop here.